Alright, welcome to another example for our double integration method. Here we have a simply supported beam with a roller here at A, a pin here at B. The span is of length L, and then there's two external moments being applied here at the roller A. There's a moment going clockwise here, and then there's a moment m/2 going counterclockwise here at B, at the pin. And our question, the problem asks us to find what our maximum deflection is. What is our maximum deflection along this span? And we know that the maximum deflection is going to occur where the slope is equal to 0. Slope of the elastic curve, or the deflected shape, is equal to 0. But before we figure out all this, we need to use our double integration method formula. D squared y over dx squared is equal to m over ei. But before we even use this equation, we need to figure out what our reactions are. And that's how we're going to find our internal moment equation for the span AB. So let's do that. Let's figure out what AY and BY are. And let's do that in blue. So what is AY and BY? And the reason I'm not finding BX is because BX is a horizontal force. It's an axial force within this pin on this beam here. So it's not really going to contribute to the internal moment. So if we took the summation of moments about point B is equal to 0, and I said, okay, this way is positive, I can say that this external moment m/2, and that's one moment. Then I have a moment going the opposite direction, and that's minus m. Then I have this AY, which creates a negative moment. AY times length L is equal to 0. And if I solved for AY, m/2 minus m is equal to AY times L. If I divided both sides by L, I'll get AY is equal to m/2L, and this becomes a negative, right? Because m/2 minus m is just negative m/2, and then divided by L is this L right here. And if I did, actually, you know what, let's not even worry about B, because I'm going to cut this beam at some distance x, and I'm going to look at the left side. Okay, so if I did that, we need to figure out what this m is so we can plug it into our moment equation, or our double integration formula. Right? And m is your internal moment, and that moment is in the form of an equation, and that equation will tell us what our moment is at any point between A and B internally, right? So if we cut here, let me draw that span again here. It's gonna look something like this, and it has a roller here, right? And the reaction there, I'll just do it in black here, is negative m/2L. And then you have this moment being applied, and then you have the cut here, and the internal moment, let's just do in let's just call it, what should we call it, let's call it MI for internal moment, internal. So, and this distance here is x, right? So if I did the sum of the moments at point O, and point O I'll just call here, is equal to 0, and I said, okay, this way is positive. I have this internal moment here, mi, then I have this negative m minus m, and then this is going up, so it's going to cause a negative moment, so negative force, right? And that's a negative, oh, that doesn't look too nice. This should be a negative m/2L times x, and that's equal to 0. And if we solve for mi, we should get m minus mx over 2L. m minus mx over 2l. Okay, so we figured out what our internal moment equation is. Now we need to plug this equation back into here, and then we can use this information to figure out what our maximum moment is. So let's do that. Let's plug this mi back into this double integration method formula thing here. You have d squared y dx squared is equal to m, and I'm going to bring this ei to the other side, right? So I'm going to put an ei here first. That way it just doesn't get messy. So m minus mx over 2l. And remember, if we integrate this formula once, we're going to get an equation for our slope. So we'll get ei times dy dx, and dy dx, remember, is just your slope or your rotation. And if we integrated m, it'd be mx, right? Minus, you have this m over 2l, and then you have the integral of x, which is x squared over 2, plus a c1, because you integrated once. You need a constant there, right? So, actually that went too far down. Let's put it right up here. It won't stop. Okay. So, we have this formula. We integrate it. Let's simplify down a bit. ei dy dx is equal to mx minus mx squared, and then 2 times 2, that's 4, and then you have this l plus c1. Okay, so I'm going to call this equation 1. And if we integrated this equation one more time, we'll have an equation for our deflection. So let's integrate this really quick. If we integrated all of this, we get ei times y is equal to the integral of mx dx minus the integral of mx squared over 4l plus, alright, this is dx, plus c1 dx integral, right? So we get ei y is equal to, well, that's m times x squared over 2 minus m over 4l times x cubed over 3, right? M over 4l is just a constant, plus c1x, right? So, oh, and then we need a second constant of integration because we integrated a second time, so I'm going to call that c2. So if I simplify this down one more time, ei times y is equal to mx squared over 2 minus mx cubed over 12l, right, plus c1x plus c2. I'm going to call this equation 2. Alright, so in the next video we're actually going to apply some boundary conditions and figure out what our two constants of integration are. And then once we have those figured out, we can figure out what our maximum deflection is along that span AB. Alright, so see you in the next video.